1.
Good morning and welcome to Evaporation 1E. This is session number 5 on evaporation. In the previous session, we learned a procedure to size an evaporator, that is to determine the heat transfer area, as well as to calculate material and energy balances. It was left to you to study in depth that method as explained in the textbook and apply that method. I suppose that you enjoyed the calculations. Although you enjoyed it, of course, you might have observed that the procedure is actually abstract. It doesn't have a strong theoretical foundation in chemical engineering, but it has enough scientific merit. That's why it's found in our textbook. I derived a new procedure. I developed a new procedure which is a bit easier to grasp, easier to understand, and I'm presenting it in this presentation. I'm showing it in this presentation. Now, to illustrate my new procedure for heat transfer area, mass and energy balance calculations for multi-effect evaporators, I would like to use the same problem as that presented in our textbook. You can pause this video to have a clear understanding of what is required from us through this problem. Now, let me explain to you the method that I have just developed. In order to solve the problem, one has to gather the equations which form the model of a multiple effect evaporator. The method is applicable to a double effect, triple effect, 4 effect, 5, any number of effects that you have. I would like you to take note of the labeling. We call MF, mass flow rate of the feed. Delta H2 VAP is the specific enthalpy of vaporization of that stream. So delta H2 VAP is calculated at T1 as temperature. Delta H3 VAP is calculated at T2. Then we are going to have delta H4 VAP, which will be calculated at T3. That is very, very important. Now you have the arsenal of equations which are used in the triple effect evaporator model. We are familiar with this. Feel free to pause the video to have a closer look at those equations. So now, in my method, I suggest that you come up with a system of 6 equations and 6 unknown as follows. These equations actually are a combination of equation 2 up to 10. I equate Q1 as found using this equation to the same Q1 obtained using another equation. So combining or rearranging equation 2 up to 10 one can come up with the system of six equations and six unknown. So my method is based on the solution of the six equations, which I'll show you later have got only six unknown. That is number one. Number two, the method is based on the fact that instead of finding the thermodynamic properties, the thermophysical properties of water, which is the solvent, using a steam table, we are going to use some correlations, and those correlations will contain some of the unknown of our problem. Now, the assumptions used in this method, this approach, the assumptions are the same as what we discussed previously when looking at the general, the general model for evaporators. But here, I'd like you to take note of the fact that we consider that there is no rise in temperature. Now, let us solve the problem. To solve the problem, you have all the data which were provided. You have all the data which were provided to us, heat transfer coefficient given to us, feed flow rate and stream composition, feed temperature, steam and third effect pressures, solid heat capacity. Now, we are going to use various uh, correlations found in the literature to determine the saturation temperature as well as different enthalpies, which are found in that system of equation. Now you have here some important correlations for TS. That correlation was taken from the literature. You see, so you don't need anymore your steam table. You can use these correlations, knowing the pressure of your steam or your pressure of your stream, and knowing PC being the critical pressure. To understand the meaning of each term or factor in the formula, please check this. Now, still in from the literature, we have a formula for specific enthalpy. We also have the formula for enthalpy of vaporization taken from reference 3. You'll discover the reference later. And to determine the specific enthalpy of saturated liquid, we subtract the enthalpy of the enthalpy of vaporization from the enthalpy of saturated vapor. Now, the specific enthalpy of concentrate are given here. Now, once we are familiar with all those correlations for enthalpies, we can move on to preliminary calculations from information provided to us. We can readily find the mass flow rate of stream number 3, which is the final concentrate. We can calculate TS from equation 2.1 and T3 from equation 12b. Let me repeat that one. We can calculate TS from 12a, and we can calculate T3 from 12b. And this now will lead us to solving the equation, the system of equations. We use a method that we know. Remember that we have those six unknown, and if you use the problem in the textbook, this is what you're going to have as final result. So let us make